Thank you very much. I'm a bit late because I thought my talk was in the afternoon, so I'm very sorry for that. So, in this presentation, we'll hear a lot of things you already have heard this morning or yesterday. So there will be no big surprises, except on one specific area. I will push the limit one step beyond everything you already have seen so far. So let me start with, let's say, a notion that you already heard about. This is about the very famous Cambrian Explosion that we start seeing now in the semiconductor world, more especially in the microprocessor area. So I took this slide from Steve Scott, who is the Cray CTO. And I like very much the picture. It explains very well on one image what we are talking about. So what's going to happen in the next years for exascale system and for post-exascale systems? And everything I'm going to describe in the first part of this presentation will be to describe the consequences of extreme specialization on how we can solve the complexity that was extremely well explained in the previous presentation. So if we look at the hard facts, what did happen over the last 10 years? So it is almost the same introduction as the presentation we just have heard about. So 10 years ago, and this is the real numbers from the top 500 list, we had only one system with an accelerator in the top 10, and it was EPI Accelerator at that time. And through time, we got more and more accelerators, and now all of them, I think, out of the 10, 8 are based on GPUs. No, there is 1 or 2 in China, not based on NVIDIA GPUs. And it's very likely that in the next couple of years, the top 10 systems will be except on the post-K machine. So there will be 9 systems with accelerators and 1 without accelerator. So I will not comment very much about the consequences. I prefer to ask one question, it's why? Why are we in this situation that makes the life of developers and end users very complex? So obviously there is the very famous end of the Moore's law, and again this is something that just has been discussed in the previous presentation. But this is here from a different perspective. It's not the consequence of the users, it's why are we arriving in a situation where we have so many accelerators coming up. So first, we are not arriving yet at the death of the Moore's law, but we are not far. We start seeing manufacturing process in 5 nanometers in Taiwan, and in production, I mean, in pre-production phase. And TSMC has already announced for 2025 3 nanometers, and they have some prototypes working in 3 nanometers. It's amazing. But even TSMC claims that beyond 3 nanometers, they will start reaching hard limits at the physical level. And beyond the question of the quantum effect at the physical level in the silicium, they are reaching as well the financial wall. The cost of a factory in 7 nanometer is about 20 billion US dollar. For a 5 nanometer factory, it's about 30 billion US dollar. For 3 nanometers, it's about 40 billion dollar. So to recover from the investment, it's going to take longer and longer and longer. So before moving to the next manufacturing process, they need first to recover from this investment. So the limit will come one day, maybe later than we expect, but the gain in the manufacturing process will not be each and every 18 months anymore. We can forget it. That will be maybe by 2030, maybe 40. But now we are at 7 nanometer in mass production. There will be 5, there will be 3, maybe 2, but not before 2030 or even 40. This is a prediction because of the financial world, not because of the technological world. And because of the end of the Morse law, there are also many people considering that we should live in pack, and it's going to open many new perspectives on the way we have to measure the systems and to invent maybe new metrics, which are maybe more based on what's going in parallel to come with big data and the consequence of big data coming from the IoT world. You have sensors everywhere in this room, in the building, in the city, and it's going to produce massive amount of data where we have to analyze maybe in real time. So that is something very, very important to consider. This evolution of big data is also what we call now in modern words artificial intelligence. But I don't see why statistics should be considered as something intelligent or artificial. This is just statistics. So anyway, this is a philosophical debate. I will not go into the details about it. But when we look at the consequence on the systems, so before we had the so-called artificial intelligence in the supercomputers, life was easy. So we had the theoretical models, and from the theoretical models we developed applications, and we obtained results. It was cool. We had big systems, monolithic systems. Life was easy. Now, if we consider big data, artificial intelligence, we start seeing workflows coming up, where we have on the top the classical HPC models with theoretical model, HPC applications and results. At the bottom of the slide, big data, and from big data we build through deep learning, artificial intelligence models, and we also obtain results. And we start mixing the two all together. The output of one model becoming the input of the other one, or in the different steps of the whole process, we start mixing classical models with artificial intelligence results and models. And what is done in the US on the Summit machine is extremely interesting from this standpoint. We see lots of fascinating models where they start mixing the two models together in preconditioners, in post-processing, and it's extremely interesting to observe because it could have very interesting consequences for the future. So if we look at the future now, there is something that we have to consider, that the classical world based on big monolithic systems that we have in a big supercomputing center, like here, it's next door, and what is done in Kobe is extremely interesting because it's still classical and very big. But we start having more and more data coming from IoT, coming from edge computing, and also we also have now many models where one part of the compute flow goes in the cloud and one part in house systems. So we have to mix all of that together in very complex workflows. So how does it match with the current systems? So by the way, before moving forward, we can consider that what we observe in the US, in China, and also in Japan is a very good example of this model, and this is a very classical model at the bottom. So basically, the machines are very monolithic. At the upper level, all nodes are equivalent and similar. For instance, Summit, which is a very interesting system, at the upper level, all nodes are strictly identical. So it's a monolithic machine. Okay, inside the node, you've got a combination of CPU plus GPU, but anyway, it doesn't change the fact that all nodes are strictly identical. This is something that could be a limiting factor, especially considering, and this is the ARM logo that you see here, that the data produced by IoT or in the edge, and more compute in the cloud, are produced on ARM sensors or edge computers are now also in the cloud. If you look at Amazon, for instance, they are moving to ARM-based clouds. In China as well. So this is very interesting to consider that, except in HPC, where you only have a few systems with ARM, the world is ruled by ARM. And that's very interesting because we have to move to ARM because of the data coming from the real world. So what's going to happen in the future? Workflows, 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 and workflows. And because of that, at each and every step of the workflow, you need to specialize the compute engine. This is the only way to get the most optimal performance per watt ratio. Can we imagine that for post-exa something system, I wouldn't say post-exaflop because it doesn't mean anything in my view. Let's say the post-exascale systems, if we want to fit in reasonable compute power, let's say between 10 and 30 megawatts, we need to specialize the hardware to optimize the way we use each and every watt for reaching a result or for computing something. So it means that we could have some legacy systems. When I say legacy, I mean x86. Okay, do we still need x86 in the future? I don't know. It's an open question, really. I believe that ARM will be the winner on the long term for the next 10 years at least. But anyway, it's a different story. And in Europe, we have a vision where there will be different combination. One module with, let's say, pure legacy system. One module with ARM processor driving classical GPUs. Or it could be with the European Accelerator, codenamed Titan. Or it could be with FPGA. Or it could be with neuromorphic accelerator. And so on and so forth. On this, it was extremely well described in the previous presentation as well. But here it drives to the level of complexity that was also extremely well explained for the developers. So how can we start at the physical level, at the hardware level, to make the life of the developer easier? So at first, we have to consider that if we have one CPU type to rule all different class of accelerators, that would be one level of complexity we can remove. We can remove that parameter from the equation. So instead of having different combination of CPU and accelerator, having always the same CPU with different accelerators, one accelerator per module in the big solution, that would be something that would help a lot the developers. And when I write compiler in the green box, this is a very simplistic keyword to mention let's say, the user environment. And for instance, one module could be a system of the size of the Summit machine. In an Exascale machine, the Summit machine is just 1/10 of a global machine. So 10 modules of the size of Summit machine for each module is something that is quite significant in the future, with a lot of specialization. So how does it look like from the developer standpoint? So a cup of coffee, a screen and a mouse, and the developer can work. So the developer needs to have a very decent programming environment. So there are many different combinations. And again, we have not synchronized our presentations, but indeed, we had exactly the same keywords in our presentations. I would say that the European perspective is much more OpenMP and OpenCL centric. But anyway, this is the concept that is behind the keywords is quite simple. The front end is the same, whatever the different accelerator. Only the back end of the compiler or the programming environment is specialized. Okay, you could lose some percentage of performance because you develop only once. But who cares at the end of the day? Because you work with very complex workflows. You have to manage different class of accelerators in your workflow. So if you have to spend 6 months in each and every step in your workflow, no way you can develop something and you can produce scientific results. So it's better to get something easy to use. Okay, you accept also to lose 5%, 10% of performance, but at least you can work, you can produce results, and you can produce scientific papers. That is more important than getting the ultimate bite of performance out of your system. And the backend should be developed by the accelerator designer and vendor, whose goal would be obviously to get the most optimal backend for the different programming languages or pragma, like OpenMP, like Exascale, and obviously in the European vision, the CPU is based on ARM, the code name of the European processor I'm going to talk about in a couple of minutes. The code name is REA, and this is the Greek mythology. There is nothing quite surprising in the European vision. And as a matter of fact, if we look at the Intel overall strategy, this is exactly what they are implementing. If you look at what they are doing with their own developments, and x86 is very centric in Intel strategy, obviously. Obviously, this is where they make their money, and this is where they are coming from. So they are developing their own accelerators with Arctic Sound, with CSA. Right? CSA is more exploration, but it's quite interesting. And they are investing massively in many different accelerator companies. Either they have acquired some accelerator companies, either they are investing. So they are considering this very seriously. And for the interface, they work with CXL, and they have announced a lot of very interesting features for CXL, and there is a massive adoption by the industry of CXL. And in terms of user environment, obviously, Intel has developed maybe one of the best, or even the best compiler in the world, and they are also starting to invest on one API, whose goal is to unify all the different accelerators. So if we look at the profile for Exascale solutions, so the main changes that we observe is hybridization at each level, hardware, software. And we need to adopt a holistic perspective from the IoT to the supercomputer, because everything will be more and more driven by data. Modularity, where we have different combination of CPU and accelerators, is a must-have for the future. The compute power will come from the accelerators, no doubt about it. And typically we get one accelerator per module in a big supercomputer. And as I mentioned, so the performance comes from the accelerator, there is no discussion. But anyway, the CPU shouldn't be weak, because there is always one part of the workflow or the application that has to work on the CPU. So the CPU has to deliver very decent performances. And in my view, a decent performance is the one you can expect from the Fujitsu A64FX. This is a very decent CPU, and this is typically what we need for the future. So it has to be very flexible, and it has to be based on the ARM instruction set to avoid any let's say, breach in the data integrity from the data creation in the IoT world to the supercomputer. And if we want to keep the architecture simple, and to use a very famous word, we need to have one CPU to rule them all, considering that all are the accelerators. And if we can adopt this position, then the life of the end user should be much easier. So how does it drive the developments of the European technology? Because all this long introduction is just to mention this. We are adopting in Europe a concept of having a common platform, and this is the consequence of the massive use of interposers on chiplets. So the idea is to develop a general purpose processor and to implement it on chiplets which are let's say, implemented on interposers. And on this chiplet, on this interposer, we can have HBM and we can have different accelerators implemented on different dies. And at the left-hand side, we see the global vision at the package level with the CPU, the HBM, and the different, and the specialized chiplet for artificial intelligence. But it could be something else. And just regarding artificial intelligence, look at the right-hand side of this chart. At the worldwide level, I already have identified more than 200 startups developing accelerators. How many will survive? I don't know. But at least 200 different startups developing accelerators for different class of applications. So if we can offer a good way, a very simple way to implement their IP, their technology with a CPU, that would be a big advantage for the developers and a big advantage for the accelerator designer, because they get access to the environment of the CPU. So at the physical level, how does it look like? You've got the interposer. On top of the interposer, you've got, in green you've got the package. Top of the package, you've got the interposer. Then you have the different chiplets plus the HBM. And when you combine all of them together, you obtain the complete system. This is what AMD is doing. This is what now everyone is doing, and this is exactly what we are doing in Europe as well. So on the first chiplet, we implement the ARM CPU. On the second chiplet, we could implement obviously a second ARM CPU with a die-to-die interconnection, or we can implement an accelerator. It could be the European accelerator that we are developing, or it could be something else. And this is what we want to offer to the market, an open platform, an open die-to-die connection, and we are going to publish the specification of the die-to-die connection this year to make sure that any company who is developing an accelerator can implement their accelerator IP with the European processor. So you have different ways of implementing the accelerator IP, either on the same die as the CPU, either, this is in yellow, either on a different chiplet but still coherent with the CPU chiplet through the die-to-die connection, either obviously on an external connector that could be CCIX, that could be PCI Express, or that could be CXL in the future. So for the CPU itself, we work with a simple concept. We have a network on chip that is coming from ARM, on which we also plug tiles, which are the ARM Zeus core. Don't ask me for describing the Zeus core, because it's under embargo by ARM. So this is news that you will have directly from ARM in March or April. And there will be additional ties for the prototype of the European accelerator based on RISC-V. We are going to implement, we are going to implement a specific accelerator for the automotive industry for autonomous vehicles. We are going to implement on the NOC as well different FPGAs, plus some cryptographic engines, and we have some room left for having specific ASICs that we can implement as long as it fulfills the specification of the ARM NOC. So the concept is to have the common platform to integrate different IP at the tile level. So now we have external interfaces with HBM, with DDR5. It's HBM2E, also with DDR5, with die-to-die connections on PCI Express, and in the future with CXL. So, in terms of global design for REA, it's going to be a multi-core Zeus implementation with SVE, and that will be also a very, very performing data engine, in the sense that we are going to offer a very high byte per flop ratio. Again, this is to help you guys to develop applications with no effort, for having a very high fraction of the peak without any specific optimization. That is very, very important to help your life, and that will help to reduce the complexity in LLVM or in GCC, for instance. With no specific effort, you got performances out of the box. That is very important. The European accelerator will get I/O coherent on memory mode with the main CPU. The network on chip will be coherent at the cache level, whatever the IP we implement on the NOC, as long as the open platform specification are reached. We are going to implement HBM2E, DDR5, and PCI Express Gen 5 from the beginning. We have also CCIX links for SMP up to 4 sockets, and in terms of physical specification, low voltage, in order we can reduce the power consumption. And we are going to work with the TSMC N6 process, which is an evolution of the 7 nanometer process. One word about the European accelerator. We are going to build the foundations of a European accelerator with a vector engine, with a stencil engine 4x4, and a variable precision engine as well. So this is new technologies we want to validate and test before we move to the accelerator stage that will be not before 2024, 2025. So in terms of roadmap, to make a long story short, we are taping out at the beginning of next year. We'll get the first prototype in our labs in second half of next year, and everything is going well, and hopefully it's going to go well. We are going to go to mass production at the end of 2021. Yes, end 2021, so the supercomputer vendors could start producing, to start manufacturing the Exascale machines in Europe in the second half of 2022 for going to operations in 2023. So we'll get the first seed units on a PCI Express board in second half of next year, and this is something you can really consider as a development platform for the accelerator, for the general purpose processor, and we'll get the Exascale machines by second half, end of 2022 for the early systems. So in terms of ecosystems, we are very, very confident, because working with ARM opens a very large ecosystem with obviously the Japanese ecosystem. I'm focusing on the HPC ecosystem, with the Japanese ecosystem, with the European ecosystem, which is very rich and very large, and we are starting long ago to work with ARM in Europe, with the Mont Blanc projects in the US, with Sandia that is driving the effort, I think, for the US. And we're starting as well very interesting efforts in China, but because of the embargo from the US, it's a bit problematic. But anyway, we see that ARM is becoming dominant in terms of momentum and progression at the worldwide level. So for the conclusion, I would say that at the technology level, the vision we have in Europe is to have one CPU to drive all accelerators. We believe that ARM is the best choice because it offers a holistic view from IoT to supercomputers on cloud. And we are designing our solutions based on chiplets and interposers. And we are going to implement an open physical platform. And this is quite new and innovative because it has not been done before. And this is some kind of extension of the concept of open something, open software, but here at the silicon level. It's not developing IP. It's not about what we see with RISC-V. It's really about physical implementation and respecting some interface that will be open. So open is the central keyword. Open common platform, open programming models, and we aim open hardware, while anyway, at some point of time, hardware has a cost for engineering, for producing, so it cannot be open at the end of the day. As long as money is involved, it cannot be open. So we have to forget the concept of open platform because it doesn't exist. And in terms of ecosystem, which is also one of the most important keywords to keep in mind, ARM is the largest ecosystem that has a very broad vision from the production of data to the data analysis in the cloud or in supercomputer centers. We believe very much in GCC and LLVM as opposed to proprietary compilers, OpenMP, OpenCL, and all open accelerator developments. And this is the end of my presentation. So I will be very pleased to welcome you in Paris, mid of March, for the first European Processor Initiative Forum that will stand on the Champs-Élysées, and the picture is really on purpose. This is a conference center that is 100 meters away from the Arc de Triomphe, so you're welcome to join us. And there will be very senior people on keynotes coming for the forum. And obviously, you can follow us on our website, on LinkedIn, on Twitter, on our YouTube channel. So we try to be modern. So thank you very much.
Thank you very much.